that one equation is that it doesn't involve x. Y prime does not depend on x. How is that reflected in its slope field?
Any value of, or any y value, like a whole line across, it'll all be the same value. Or any line of x, I guess. Like if you say that x equals, or y equals 3, that all those values are going to be the same.
So if y equals 3, then you got the same slopes all the way across because y prime is a function of only y alone. Yeah, interesting. Oh yeah, on those integrable ones where it was just a function of x, the first example we saw, at any fixed x, the slope was always the same. And so any graph with a vertical translation satisfies the same one, right? So if the differential equation is a function of y only, then you'll see that for a fixed value of y, you get the same slope segment all the way across. Function of y only, does not depend on x. Okay, so that's good exercise in matching, and you can expect problems like that, quiz, exam problems. All right, let's mosey on into the next topic. We're going to look at section 1.4. In 1.4, yeah, we're going to be talking about a certain class of first order DEQs again. So one class of differential equations that can ordinarily be solved exactly are separable equations. Okay, separately. And to define what that means, a differential equation is said to be separable if it takes on a specific form. If it can be written in the form dy dx equals some expression involving x times some expression involving only y. Okay? So what this means, in other words, is that if your equation can be factored, so this is a multiplication, factored in such a way that you have an expression involving x alone times an expression involving y alone. So in other words, if those variables can be pulled apart into two expressions that are multiplied. So that means the expression on the right, expression on the right is factorable as some expression involving x times some expression involving only y. Okay, so an example of some of these. Say the equation y prime equals 2xy squared. Okay. That would be separable because we have 2x times y squared. This is like a little f of x in our formulation there. That's our little g of y. So two expressions that were multiplied together on the right side of that first order differential equation. Another one. This is separable. Y sure doesn't look like it. It doesn't look like it's factored at all. We got plus, that's a plus. So they don't always come to us in a nice form on the right. But if we rearrange this, we can write, well, first x dy dx equals 1 minus y. And if I go further, if I divided both sides by x, then we can write dy dx as 1 minus y over x. Does that look factorable as some expression in y times some expression in x? How? Yeah. Oh, I could write this, I could think of the whole numerator expression, right? 1 minus y. This is 1 over x times 1 minus y. So that would be separable. In other words, if I could separate those variables, factor them, okay? So some expression involving only x, some expression involving only y, then it's separable. Okay? All right, so there is a pretty direct method of solving these. Well, direct in the sense that, well, we can take advantage of integration like we could with integrable first-order equations. All right, so we solve these by separating the variables. On either side of the equation. Oops. And then integrate it. So, an example, say we got y prime equals 2xy squared. That was that first one. We can write this as, well, dy dx equals 2xy squared. And we can operate with these, what's called the differentials. Okay? We want to get the dy and the expression involving y on one side, and we need the dx on the other side with the x terms. Yeah. Yeah, you can divide both sides by y squared and multiply, think of it like multiplying by dx. And you can write this, let's write that out. Well, dy over y squared. We need to get the expression involving y with its differential equals 2x dx. So integrable, well, we'll talk about that in a minute. And then we integrate both sides. Okay. So it's separating by pulling apart those factors onto either side of the equation so they are with their, now I do need the dx in the numerator. We need to bring it out. It needs to be times. dy, sometimes you see integrals like this. I don't like it. I like 1 over y squared dy, but we can deal with that. All right. So this would be like, I'm going to write this, is this okay? Y to the negative 2 dy equals, and what's the integral of 2x? X squared plus some constant. Okay. Now, integrating y squared with respect to y, or y to the negative 2, what do we get?
1 over negative 1 over
y to the negative 1 divided by negative 1, or equivalently times negative 1. Okay? Plus some other constant. Now, here's the deal. If I have plus some other constant here, and on the other side, I also have an arbitrary constant of integration.
Do they cancel?
Well, it's not, they don't necessarily cancel because they're not the same. They're not the same. Just combine them and say it's just an arbitrary constant, right? Subtract the other one to the other side, and it doesn't really matter what I call that because it's an arbitrary constant. Any constant will do. All right, so you don't really have to do much tracking of this, but just to make it clear, I just said C2 is C minus C1. But it's still just an arbitrary constant. One subtracted by another. Any real number could come from that. Okay, good. Now we can solve this. Well, I could multiply both sides by -1. Y to the -1 equals negative x squared plus C2, or minus C2, it doesn't really matter. Okay? So, solving this further, I could say, we're lucky on this one, I could solve for y, raising both sides to the -1 because that would solve for y alone, right? We'd have 1 over negative, I'm going to pull out the negative, x squared plus some constant. And this is what's called an explicit solution. We have y in terms of x. Now, we won't always be so lucky as to be able to solve the resulting equation for y. Okay. All right. So let's do another one. So a note on that, yeah, we may be able to solve the resulting equation. But often it's not possible. Well, not as an integral. Maybe you can integrate that side, but then I don't have something that I can solve for. We'll look at an example real quick. Often it's impossible. And when you leave it and it's not solved for y, we leave it in what we call implicit form. Okay. All right, so an example of that. All right. So say 4 minus 2x over 3y squared minus 5. Now, it doesn't look like it's factorable, but numerator and denominator are, one involves only x, the other involves only y. You can think about this as 4 minus 2x times 1 over 3y squared minus 5. So it really is factorable. Okay. Now, a quick way, sometimes we're lucky if the expression in the denominator involves only y, then we can imagine cross-multiplying this, right? Multiply both sides by 3y squared minus 5, that gets it over here. Multiply both sides by dx, that gets it up there. Okay, so we have 3y squared minus 5 dy equals 4 minus 2x dx. All right, so we've separated the variables. I got my x's and my dx on the same side of the equation, all my y's and the dy on the other side. Then we integrate with respect to that variable present. Okay, and what do we get on the left? Y cubed minus 5y plus some constant. But here's what I'm going to do. I'm just going to imagine collecting all the constants and just saying plus c on one side. And what would I have on the right?
4x minus x squared.
4x minus x squared plus some giant arbitrary constant of integration. So this is implicit form, right? We got y cubed, we got y, we got some x's. Now, not too easy to solve this for y, is it? I could factor a y out of this, but then I still got a y squared minus 5. Okay, that's a cubic equation in y. There's really no good way of solving this. Well, then we'd come up with that differential equation again. So we would go in reverse, right? Yeah. So this defines the curve. It's just implicit. It's just an implicit form. One thing I could do is say, well, if I got everything to one side, y cubed minus 5y plus x squared minus 4x equals some constant. This is implicit form. Okay? All right. Now, say, for instance, that if we had an initial condition, we might be able to find what that constant is, right? But check out this example 2 in 1.4, page 34. Okay, so we did example 2. All right. So we can solve it to here. This equation is not readily solved for y explicitly as a function of x. And if you graph it for different values of constants, look what you get. It's not a single function. An implicit equation like this could give you some weird shapes. So each one has a different value of c. Now, if you did take Calc 4 recently, awesome. Because what you might notice is if I collect everything on one side like we did and you get a constant over here, then you could think about this as a function of two variables. Okay? And for a particular constant, this would be thought of as the contour line of this function, of this surface. It's a two-dimensional, it's a graph to be a surface. So any particular constant would give you a contour line of this surface. Okay? Yeah, kind of trippy, right? A function of two variables, if you get everything over there, equal a constant. So setting the output constant equates to contour lines.
The contour line is like a slice of a three-dimensional?
Slice parallel to the xy plane. So all at equal level, they all have equal function values, as if we set this equal to a constant up here. Anyways, so interesting relationship to Calc 4 and surfaces. The best we can do, so if you have an initial condition, y of 1 equals 3, you can solve that, put x equal 1 and y equal to 3 in that equation, and you'd come up with 9. Okay? What that means is that at the point 1, 3, you get this curve, although that's not a single function. So you might only get a function between -1 to 4 or something like that. Otherwise, it's multiple functions adjoining with each other. It doesn't pass the vertical line test, not a single curve. Okay? Okay, what time do we got? We got about 20 minutes. Yeah, I want to point you to this in 1.3. We didn't really talk about it. Ugh. But when you're reading 1.3, existence and uniqueness of solutions. Someone asked about this the first day. They said, okay, well, if I got an initial condition, how do I know there's only one solution to that? How do I know that there's even one? And if there is one, how do I know that there's only one solution? So this gives some conditions for which there does exist a solution to an initial value problem, and when it guarantees uniqueness. Okay? So, if you have an equation, first order of the form, if you have a first order differential equation and some expression in x and y over here, then there are conditions where you are guaranteed a solution and that solution is unique. So if the function on the right of this is continuous and its partial derivatives are continuous on any rectangle that contains the initial condition point, a, b, so if y of a equals b, then there will be some interval I on the x-axis containing the point A. The initial value problem will have one and only one solution that is defined on that particular interval. Okay? So that example that we looked at on page 34, right here. So this would be the little f of xy on the right side of the first order differential equation. Now that would be continuous as long as the denominator does not equal 0. That happens at particular values of y. Okay? But the point 1, 3, it would be continued. This would be a continuous function at 1, 3. So that theorem guarantees that on some interval on the x-axis, there will be a unique one and only one solution to this differential equation. Now, it may only go from x equals -1 to x equals 3 or something like that. Beyond that, the function may be discontinuous, so certain values of y, okay, wherever the denominator is 0, it would be discontinuous. But there is a solution. That function may only, the solution may only exist on a small interval on the x-axis. As soon as it goes vertical and bends back in, that's no longer the same function. Okay. Defined implicitly, you can get some crazy curves like that, but that is not one function through that point 1, 3. Okay? So read over that and mull it over the weekend, that theorem, existence and uniqueness. Okay, for now, I want to do a little bit more practical problem. All right. And for this one, I want to go back to Newton's law, revisit Newton's law of cooling. All right. So say a cup of coffee, we pour a cup of coffee, and it's poured at 130 degrees Fahrenheit. Okay? In a room kept at a nice, comfortable 70 degrees. Okay. After 15 minutes, that coffee in the cup is down to 95 degrees. So I want to do a couple things with this. First, I want to write the corresponding differential equation that models the temperature over time. Okay, so a couple things. We want to let's just define T of T to be the temperature of the coffee at or after T minutes. So we got to define our variables. And Newton's law of cooling, what was that? Yeah, the rate that what the book calls the time rate of change of temperature. Okay? So the rate of change of temperature with respect to time is proportional to something. Proportional to not just the temperature of the coffee, right? Because, well, the hotter the coffee is, we don't want to be just difference. Difference of temperature of the coffee and the ambient or surrounding temperature. So that would be our A in what the book used as A in this model. So T minus A. Now, they said, we put this negative in front of k, so we knew that k had to be a positive value. So we have negative k times t minus 70. Okay? We know that the coffee starts off at 95 degrees, so 95 minus 70 is always going to be positive, right? Times a negative, so our derivative should be negative. So that's our differential equation that models this situation. B, let's solve this. Okay. All right, so this is separable, and you might notice there is no little t at all. Where is that? Doesn't it have to be factorable as some product of the independent variable times the dependent variable? But all we have is a negative k, and we got a t minus 70, right? Well, this is the expression involving capital T, and the other function just happens to be a constant. Okay? So we can separate that. Still, it's just that there will be no mention of the independent variable t. So, and multiply both sides by little dt, and we have just negative k dt, right? So it is separated. It just happens that, okay, my function of t is a constant function. Now, when I integrate both sides, what do we get on the left? Right. Now, you could do it. You could do a substitution. Let u equal t minus 70, and we have 1 over u. And what's the derivative or integral of 1 over u with respect to u? Natural log. And then you go, oh, well, u was just t minus 70. What we end up getting is just natural log of t minus 70 in absolute values, technically. Okay, depending on whether t minus 70 is positive or negative. And what's the integral on the right? Yeah, constant, so it's just negative k, and it picks up a t. Plus some constant here. Okay. All right, now what? We can solve for t. Yeah, and one way to think about it, if natural log of this equals that, then e to that has to equal this. Or think about taking e as the base and raising both sides to that power. The e and the natural log knock each other out. We get t minus 70 equals e to the negative kt plus c. And is it okay if I write that as e to the c because those powers are bad? Yeah?
Can you write that as a or another?
Right, right. Now this is just a constant. So I could call it C1 or something like that, whatever it is. I don't want to call it A because A in this, they used A to represent the ambient temperature, so I'll call it C1, e to the KT, negative KT. Okay. Now we can make an argument here that, you know, if I want to try and find any of these constants, right, either one of those, I have an absolute value here, but what's the initial temperature of the coffee?
130.
130. So 130 minus 70 is a positive number, and these absolute values are unnecessary. They're unnecessary because this will always be positive. Okay. So one thing to note is that T starts off at 130. T minus 70 will always be greater than 0. So the absolute values become superfluous. In other words, absolute value of a positive is just itself. So we can abandon or disregard the absolute value in this case. If the coffee was coming from 30 degrees, if it was frozen and we left it out, then the temperature of the coffee minus room temperature would be negative. That would be a different story. So we can disregard the absolute value, and we get T minus 70 equals, I'm calling that C1 e to the negative KT, right? So we got some exponential stuff going on. If I solve this for T, we're almost there. Add 70 to both sides, we get 70 plus C1 e to the negative KT. Now we want to use some of our information. We know the initial temperature of the coffee. So that implies, when I plug in 0 for T, we get 70 plus C1 e to the 0 times anything is 0, right? And we know that that has to equal 130. Okay, so T of 0 equals 130. And luckily for us, e to the 0 is what? 1. So we just have an equation that involves this constant C1. We get 70 plus C1 equals 130, so that C1 must be equal to what? 60? 60? Yeah. Okay. So now we're even closer. I know that T has to equal 70 plus 60 e to the negative KT. We still don't know one thing. What's that? Right, K. So notice that given just the initial temperature of the coffee, doesn't tell me anything about the rate at which it's cooling. That's just a point piece of information, point value. Temperature at 0 is 130. Well, I don't know if we're talking about coffee in a room that's 30 degrees or if coffee that's in a room with, 90 degrees. That tells me nothing about the rate that it changes. Now, having a second piece of information, after 15 minutes that coffee is cooled down to 95, that will allow us to find the cooling rate. So we need this other info that temperature after what, 15 minutes? T of 15, after 15 minutes the coffee would cool down to 95 degrees. So T of 15 looks like e to the negative k times 15 must be 95. Okay, so then we solve this for k. Now, the problem is that's up in the exponent, isn't it? So, yeah, we're going to use a log at the end of this. That's all right. Subtract that 70 from both sides. And we're going to get 60 e to the negative 15k